In this video, we just want to quickly go over handout number 4. And really, there's two goals in this set of 12 or 13 slides. Remind you about orbital naming like S and P and D, and talk about how to generate electron configurations for atoms. So overall, this is still more information than we typically are going to need for organic chemistry, since we're mostly talking about connecting atoms like carbon, hydrogen, nitrogen, oxygen. We don't need to get as in-depth with regard to electron configuration stuff, but making sure we have that basic knowledge in place will ensure that the next section, the next handout, chapter 1, handout 5, makes sense. So something that you hopefully remember is that there are different orbital types for our atoms. S orbitals, for example, which are spherical orbitals, and depending on what the number is out front, that's going to dictate really how big that orbital is. So you can see here we talk about a 1s, 2s, and 3s orbital. So that number out front is really telling us what row in the periodic table we're in, but also how big that orbital is. So I always think when we're talking about S, that's to remind us that it's a spherical orbital centered on the nucleus. And then like it says here, the radius of the sphere increases with the value of n, which, as I said, correlates with the row we are in the periodic table. That should make sense because as we go farther down the table, the size of the atom increases, and that's because the size of the orbital is increasing, meaning the distance from the nucleus to the outermost electron is increasing. We're mostly going to be interested just in s orbitals and p orbitals for the purpose of looking at atoms like carbon, nitrogen, oxygen. Hydrogen just has one s orbitals, but s and p orbitals should mostly take care of what we wanted. It's talking a little bit about the quantum number stuff, and if you remember any of that from general chemistry, really not going to matter here. I just want you to know the shapes of the orbitals and how we generate electron configurations, because that'll matter a little bit later. When we talk about s orbitals, they're spherical. When we talk about p orbitals, it's going to have two lobes, either above and below the xy plane for z orbitals, in front and behind the yz plane for px orbitals, and then in front and behind the xz plane for py orbitals. So for any value of n, meaning a particular row in the table, again, there's going to be 3 distinct p orbitals. And remember, each orbital can hold a maximum of 2 electrons. So for now, right, just to make sure you remember, s orbitals are spherical, and p orbitals are going to have these double lobes. That's kind of the most critical information for us to have. And always when we're talking about orbitals, each one can hold a maximum of 2 electrons. And like I keep saying, right, I'm still providing you more information than we really need for what I want to do in the rest of this chapter, but just kind of making sure we're all on the same page here. D orbitals are going to be less important for what we're doing here. Again, you don't need to worry too much about what it's saying with regard to the quantum numbers. That's not going to be too critical here. Same thing, each orbital can hold up to 2 electrons. D orbitals kind of, all but one of them kind of look like double p orbitals, so 4 lobes oriented in different ways. You can see this one here and this one here almost look identical, but if you look more closely, they're rotated 45 degrees relative to each other. These guys, the lobes are between axes. These guys, the lobes are cut through by the axes, but generally the same shape. The outlier is this one. And so remember, when we're talking about orbitals, these are the volumes in space that electrons are permitted to occupy, but mathematically what they represent are solutions to the wave equation and the electron densities resulting from each one of those wave equation solutions. So again, physically representing the volume in space electrons are allowed to occupy, but mathematically coming from solutions to the wave equation, and then the square of that will give us the volume in space that we're observing here. Still, more information than we're really concerned with here, but that's kind of what I wanted you to see. So for completeness, we looked at s, p, and d orbitals. There are other orbitals, but we're really not worried about those. And in fact, mostly our concern is just going to be about s and p orbitals because of the atoms we're particularly interested in talking about. So this is a simple energy diagram for the orbitals in a one electron system. And so what you can see here is all that's dictating the energy of each set of orbitals is whatever the n value is, whatever that number is out front. This is what things look like for a one electron atom. Typically that would be something like a hydrogen atom in terms of the energy levels that we observe. So again, if you're remembering things from general chemistry, you may have seen that equation for the Bohr hydrogen atom to calculate energies of moving between orbitals or wavelengths of photons for moving between orbitals. That was based on this model where the only thing dictating energy level is the n value. But what we find out is once there are multiple electrons in an atom, then those levels are no longer accurate. And now we get broken into subshells instead. So you can see the 2s and the 2p are separate from each other. 3s, 3p, 3d, 4s, 4p. Now things are spreading out. So this picture gives us a better idea of how electrons fill in a multiple electron atom. This is a better picture of what's going on. And we just fill from the bottom up in terms of the electron flow by using each one of these boxes to store up to 2 electrons. So we'll see as we look at filling in for atoms how this will exactly work, but this is the picture that we have. So now you know what we mean when we talk about an s orbital or a p orbital with regard to its shape, and then here we're looking at the order of things in terms of how electrons are filling in. So something that we want to be able to write for an atom is the electron configuration. And so typically what we'll see here is a number out front telling us what row we are in the periodic table, then a letter after that telling us what orbital type we're looking at, and then finally a superscript to tell us how many electrons are in that particular level. So for example, if we were talking about for p, any p level is going to have 3 orbitals. So this would be our 4p. We'd call it a subshell, all of the orbitals belonging to this notation. And it's telling us that there are 5 electrons. So again, if you remember stuff from general chemistry, we would put 1 electron into each orbital first. Don't double up till we have to. I'm putting those electrons spin up, which is technically lower in energy, and then I'll come back and double up only when I have to. So that's what 4p5 as an electron configuration would look like. 2 in the first orbital, 2 in the second orbital, but only 1 in the last orbital. And remember, we put 1 in each before we have to double up. So then as we get to atoms and we want to generate the electron filling diagram, we fill from the bottom up, and at any level we max out before we keep going. So this is lithium where there are 3 total electrons. So if we go back to our energy diagram here, we'd start from the 1s and then fill our way up from there. And when we do that for lithium with 3 total electrons, this is the configuration we get. And it would be 1s2, so 2 electrons in the 1s orbital, 2s1, 1 electron in that 2s orbital. So what we want to do when we're filling things in, technically our goal is to maximize positive spin, so more spin up than anything. But in practice, what we end up doing is filling from the bottom up. And then, like we were talking about, if we get to a point where there are multiple orbitals of the same energy, we call orbitals of the same energy degenerate, we put 1 in each before we double up. And so that's the configuration we would see there. This is describing the configuration for oxygen, which has 6 electrons. So you can count as we're doing this. Oh, sorry, 6 valence electrons, but 8 electrons total. So you can see that we've put in 1, 2, 3, 4, 5, 6, 7, 8 in that configuration. So we would write it out as 1s2, 2s2, 2p4. So that would be the electron configuration, but then the filling diagram shows us that 2 of the electrons on the highest level are unpaired. But that's how we would generate the configuration. So I want you to both be able to write out the electron configuration like this, but also be able to generate the filling diagram as well. And still, again, this is more information than we're generally going to need in this course, but it'll help you to make sense of the next thing we want to talk about in the next handout, which is hybridization. So then, I know I keep saying you may remember this from general chemistry. Don't panic if it's not stuff that's fresh in your mind. It could have been a year, it could have been much longer. That's okay. As we're going along, we'll have enough time to review these concepts. And of course, if you're really feeling like this is not old news to you at all and you need some help getting caught up, that's what I'm here for. So this is showing us essentially a periodic table, but it's now shown us the left part with the alkali metals and alkali earth metals as belonging to s orbitals, the right part with the non-metals and metalloids as p orbitals, in the middle all those transition metals belonging to d orbitals, and then down here we're not even going to worry about it, but the f block, which we see down at the bottom, which remember really goes in the middle of the periodic table, but then that makes it way too wide. So one of the tricks is to directly use the periodic table and count off of it, knowing the left is S, the right is P, and the middle is D, in order to directly get electron configurations. So again, we're mostly interested in carbon, hydrogen, nitrogen, oxygen, but this is the process that we would follow to generate the electron configurations. So I would just walk across the row, 1 electron at a time, following the periodic table, and that would tell me the electron configuration. So that's the same information I could generate looking at the electron filling diagram. Okay, here's a zoom in so you can kind of see a little bit better, just to give you an idea, right? This would be hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, etc. And so each one of these boxes represents a particular element on the table, and so I could just count it across to generate the electron configuration. So for example, right, for fluorine, I would just walk all the way across till I got to fluorine. So it would be 1s2, 2s2, 2p, 1, 2, 3, 4, 5. So that's how we use the periodic table to generate the configuration. And of course, I can keep going from there, but that covers most of what we're interested in. Okay, so hopefully this makes sense to you, how this is mapping onto the periodic table and how we generate our electron configurations. We're not really going to go past fluorine. We'll see other elements like chlorine, bromine, iodine, but we're not going to be super interested in generating their electron configurations. Okay, so then here is the periodic table, and then I just kind of mapped S, P, and D onto there. So we just figured out fluorine, right, just by counting across 1s2, 2s2, 2p5, and you can keep going on from there. So hopefully that's making okay sense to start with, just to have a handle on how we're generating our electron configurations from the periodic table. So now, knowing things like this, we can say carbon is 1s2, 2s2, 2p2. Nitrogen, 1s2, 2s2, 2p3. Oxygen, 1s2, 2s2, 2p4. And then in addition to that, looking at the outermost level, so level 2, we can look at how many valence electrons there are, and that's what's going to be most important as we go on and look at hybridization, which is our next topic. Okay, I think that's it for these. This is just a blank sheet, so we can go ahead and stop there, and then in the next video we'll look at what to do with this information and talk about the concept of hybridization and how it relates to electron configuration.